Okay, so this video is about non-ideal batteries, and so this is something that I'll need to review a few things first so that we are in a position to kind of understand what's going on. So let me start with quickly reviewing the parts of parallel circuits that I need you to know. And obviously this is good review in and of itself. A parallel circuit's a really important idea. So here I have a parallel circuit. I have a battery, I have a resistor R1, and if I choose to, I can add a second resistor R2 in parallel with it. And I want to point out that whether or not I add this second resistor here, essentially this is all one big equipotential, and that's the highest voltage equipotential, and this is all one big equipotential, that's the lowest voltage equipotential. And so resistor 1 already has access to the full voltage drop, the EMF of the battery, so V1 is going to be fixed regardless of if I add the second resistor or not. That just joins the party. But regardless of whether R2 is connected or not, the voltage drop across R1 is the same. It's just the EMF of the battery. So if V1 is fixed regardless of R2, and R1, of course, its own resistance value is fixed regardless. And so what that means, if we look at Ohm's law here, V equals IR, well, if V1 is fixed, that's the EMF of the battery, and of course this R1 is fixed, then there's no wiggle room there. The current that this branch receives, I1, is also fixed regardless of if the other resistor is added or not. And so if I1 is fixed, then P1 is also fixed. So regardless of whether resistor 2 is connected, V1 and R1 and I1 and P1, everything about resistor 1 is exactly the same as it was if there was one other branch or 17 other branches. Essentially, that's kind of the hallmark of a parallel circuit, that each branch is independent. It does its own thing regardless of whether or not there are other branches connected. Now, of course, as you do add these other branches, the equivalent resistance of the circuit does go down, and the total current does go up. And so it is a legitimate question to say, how can I1 stay the same while I total goes up? Well, of course, I total goes up because as you add resistors, because even though they're delivering exactly the same current to each branch as they would if they were connected alone, they now have more mouths to feed. There's also going to be an I2 here that needs to be supplied, and so you can think of the total current going up, not because the existing branches are getting any more or less current. They're getting exactly the same. Remember, I1 is fixed, but there's also an I2 now that needs to be supplied, and so I total has to increase to supply that as well. So that's kind of the review of the parallel circuit. Let me review the series circuit. So the series circuit, it's a little bit different. Here's the example that was from the other video. I have a 12 volt battery and then a 1 ohm and 2 ohm resistor in series. And let me remind you how this works. The voltage drops in general are not equal. The voltage drops, you're going to find that the voltage drops are more across the higher resistors. So I talked about this in the series video, about how you can think of these large resistors as bottlenecks. The largest resistances in series will have the largest voltage drops and dissipate the most power. Okay, so if you have a bunch of resistors in series, you're going to find the largest resistance in that series chain is going to have the largest voltage drop and the largest power. You can think of it as this is the largest obstruction, so it has to have the largest largest reward. So the 8 volts is kind of its energetic reward for there. And of course you have 3 equipotential regions. You have the high voltage, we'll call that A, that's up here. We have a middle step, B, that's here. And we have a final lower voltage region, which I'll call C. I forgot to circle these up here. So you have a high, medium, and low step. And so of course the entire journey from beginning to end is set by the battery as 12 volts. You're dropping it across resistor 1 and resistor 2. And so the sum of those two voltages, V1 and V2, is going to be the battery voltage. And so that's kind of a quick review of series and parallel. But here's my question. What happens if you change one resistor only? So sorry, that's hard to read. It says, what happens if change one resistor only? So we're going to mess with the resistance value of one of the resistors in the series chain. Okay? So we're not going to touch R1, we're going to leave that as 1 ohm, but we're going to start messing with R2. Okay? So let me go ahead and take a look at some examples. So in all these cases, I have an R1 and R2. I'm going to write down the voltage drops V1 and V2, and though I haven't drawn in the battery, it's assumed that the drop from beginning to end is going to be 12 volts. Now one thing I forgot to mention on the previous page, so let me go back there for a moment. So if you remember in series, the currents are the same, and so if we say I1 equals I2, there is only one current in a series circuit. If we plug in Ohm's law here, V1 over R1, V2 over R2, you can cross multiply this and get this statement. So this statement is kind of useful and informative at least for a 2 resistor circuit. And it basically tells you that the ratio of the resistances is equal to the ratio of the voltages that they take. This relationship, I don't expect you to memorize this or use this much. I want you to understand conceptually what it's saying. It's saying if you mess with the ratio of resistors, so how much of the 2 resistors are in ratio to each other, then you will also mess with how much voltage drop they each take. So mess with the resistors, even just one of the resistors. If you mess with one resistor and you leave the other one alone, it's still going to change this ratio, and so it's going to still affect how much each of these 2 takes the voltage. And remember that these 2 are still always required to add up to the EMF of the battery. So going over here, again, here's some examples. So what I'm going to do is I'm going to leave R1 alone. That's 1 ohm. So 1 ohm, 1 ohm, 1 ohm, 1 ohm. Those are all exactly the same. But I'm going to mess with the second resistor. Okay. And again, remember that there is a battery connected here. I haven't drawn it, but I'll keep it as 12 volts. So here are some examples I've computed. And again, how would you compute these? You would compute them exactly the same way as we computed this example. Okay, so you should definitely know how to do that, but that's not really my focus here in this video. I've computed some examples, and you can see what happens here. And so I've lowered this resistance here from 2 ohms, 1.4 ohms, 1 ohm, and 0.5 ohms. So the second resistor is getting smaller while the first resistance is staying the same. So first of all, if you want to, you can go back and confirm that these examples all do meet this idea here. You mess with the ratio of resistors, you mess with the voltages, you'll find that each of these ratios, so the resistors here are at a 2-to-1 ratio, so are the voltages, 8-to-4. Okay, so over here the resistors are on a 1-to-1 ratio, so are the voltage drops. Okay, so in each case the resistors are in the same exact ratio as the voltages, and of course we need both of the voltages to still add up to battery voltage, so you can see in all of these cases they do still add up to 12. Okay, so you add up the voltages here from beginning to end, they do all add up to 12. It's just how much does one resistor versus the other take. And so here's what I want you to notice about these examples, is I'm making this resistance smaller, 2 ohms, 1.4 ohms, 1 ohm, 0.5 ohms. As you decrease its resistance, you are also decreasing the amount of the voltage that it takes for itself. Okay? So remember we said that when you had a large resistor, it's going to hog more of the voltage drop. Now, because I'm making this resistor smaller, it's going to hog less of the voltage drop. And where does it go? Remember that the voltage from beginning to end has to be the same And so it's giving it to the others. So it's kind of redistributing it to the other resistors. Even though this first resistor isn't changing its value, it's still 1 ohm, because the second one is its resistance getting less, then it's taking less of the voltage drop and giving it to the other resistor, or potentially other resistors. I just have other one, but anytime you mess with one resistor in the chain, you make it smaller, it's going to make its voltage drop smaller and it's going to give it to the others. So that's what this says here. As you decrease the resistor, you're going to decrease its voltage drop, and it has to go somewhere. It gives it to others. So what I'm wanting you to see is that as I'm decreasing R2, I'm decreasing its voltage and it's giving it to others. Okay? So that's the big thing I want you to notice here. We're going to carry that going forward onto the next page. Also, I do want to point out that I'm making the resistance of this chain overall less, right? So these resistors, if I'm not touching the first one and I'm making the second one smaller, I'm definitely decreasing the resistance of the circuit overall, so there will be more total current. So the total current in each of these is going to increase, so it's going to get larger and larger, okay? So again, to summarize here, what you see is V2 is decreasing and V1 is increasing, and the total current is getting larger, okay? Now, of course, I could also do the opposite case. It's worth visiting for a second. So the opposite case is, what if you make one of the resistors much larger? Well, then now this is going to hog way more of the voltage drop for itself. So if you increase the resistance of one of the resistors in the chain, it's going to take more of that voltage and it's going to take it from others. So if you look at this example, I still have this as 1 ohm, but I have this as 11, so it's way bigger. Look at how much voltage it's hogging. It's 11 volts, and this barely gets any. So again, the kind of common theme here is if you have a bunch of resistors, they're all in series, you mess with one, okay? If you take one resistor and you make it smaller, then its amount of voltage it takes is less, and it gives it to others, so that all the other ones, even though they might be resistances, the other ones aren't changing, you're going to increase their voltage. And likewise, the opposite case is if you take one resistor in the chain and you make it really big, it's going to increase its voltage and it's going to take it from others. Okay, so here R2 is increased, it takes more of the voltage drop, it hogs more, and it takes it from others. And of course, you can compare here if you like. Again, the resistors are an 11-to-1 ratio, so are the voltages, and the voltages do still add up to 12. Okay, and again, of course, here, if this resistor gets really big, we have a very large equivalent resistance, and the total current going through this is going to drop. So let's take a look for this case, for instance, where you have barely any voltage drop across this, and you have a lot here. Here's some examples from the homework. There's a problem where there's a toaster, or toasting heating element, which has most of the resistance, and then you have the power cord, which of course has very minimal resistance, but not zero. So one of the homework problems has that situation, and the resistances are really different, and so the voltages are really different as well. Another example of a homework problem, most of the time these are your special resistors in your circuit, and that's where all the resistance is, but there is one problem that asks you to consider the fact that the wires themselves do have some small but non-zero resistance, and how much does that really affect things. So those are a couple problems in the homework that are on this case, where almost all the resistance is here and very little is here. But this is the case that I don't want to focus on. I want to focus on this top case, where when I make one resistor smaller, it gives up voltage to others in the chain. So going over to my next example, first thing we should look at is how can a resistor be increased or decreased? And again, I'll focus on a resistor being decreased. Now there are resistors that there's a dial on them, and you can literally change the resistance value. These are called potentiometers or POTS for short. But that's not really what we're looking at here. The reason why one resistor in the chain can decrease its value is not because the resistor itself actually changes at all. It's because you're throwing an extra resistor in parallel with that. Okay? And so, of course, if you look at, it used to be R1, then R2, and now it's R1, but this is the R2-3 combo. Okay? So, of course, when you add an extra branch, that lowers the resistance overall. So now, essentially, you've gone from R1 and R2 in series to R1, which stays the same, and R2-3 in series. And R2-3, that's actually a decreased value from before. And so the voltages will also redistribute. And so this now, being smaller resistance overall, the voltage drop is going to decrease. It's going to give it to the others. So the voltage over here is going to increase. Okay? So that's exactly what we were talking here on the previous page. So right here, if you decrease the resistance in the series, it's going to decrease its voltage. It's going to give it to others in the chain. Let's also look at power. Okay? So another thing we want to look at is power. So let's take a look at resistor 1. That's the easy one. The formula for power, there are several choices, but I'll pick this one. And of course, we're interested in this for resistor 1. And so, of course, resistor 1, well, that resistors haven't changed. So if the voltage across it increases, then the power is going to increase. So what we expect here is that the voltage increases and the power increases. Okay? And let's take a look for resistor 2. So resistor 2 alone, we can apply this equation as well. So we'll apply this equation to resistor 2. So resistor 2 itself, of course, this is still fixed. Yes, the resistance in this section got less overall, but it's because of R3 being added on top, the resistance of 2 itself wasn't actually altered. And so again, if that we can see that voltage goes as power goes. So if the voltage got less, then the power will get less. So here, not only will the voltage decrease, the power will decrease. Okay. So let's take a look so I guess I should label this as V1 is going to increase, V2 is going to decrease, and the power P1 and power P2. I haven't really mentioned resistor 3. Resistor 3 is kind of boring because it's off when it isn't connected, and then of course it'll be on when it is connected. So power 3, of course, is going to be, P3 is going to go from 0 to something, so that's going to increase, but that's kind of boring because of course it's going to increase. You're adding it to the circuit where it wasn't before. We're sort of interested in what's going on with the resistors that you had already in the circuit. So here are some examples of where we saw this. There was a demo in class where I actually just literally connected up 2 light bulbs and then put a third one in parallel. And we did see that this one got brighter and this one got dimmer. So that's exactly, of course, ties in with the powers, right? Power is proportional brightness. So there was a demo where I had 2 light bulbs, I connected the third one of course just turns on when I put it on. That's not interesting, but this one gets brighter than it was before, this one gets dimmer than it was before. And while I'm on the topic, I could talk about, I again mentioned the application that I was talking about there. That was to a circuit breaker. So imagine the reason why this resistor is decreasing is because you are, taking this from 1 to 17 hair dryers. Okay, you're plugging a bunch of hair dryers into a power strip. They're all in parallel, and of course, what you're going to have here is that this voltage and this power is going to decrease, and then what is in the series with? It's in series with your household wiring. And your household wiring, your voltage and your power is going to increase. And of course, this is your danger zone. So you're dissipating a lot of power and the wiring is getting very, very hot. And so you might start a fire. Let me remind you here, of course, is that the total current here is also getting very large. Remember that as you start lessening one of the resistances in the chain, the total current's going up as well. So the total current is going up, and at some point your circuit breaker says it knows how much is too much current and how much power is too much to dissipate in your household wiring, and it goes off. Okay, so that's two examples right here. Another example would be how the voltmeter works. So a voltmeter, when you have two resistors in series, and then the third resistor is actually the voltmeter. Okay, so the third resistor is this voltmeter. The proper way to use a voltmeter is to put it in parallel with the thing that you're trying to measure the voltage of. But remember that this does slightly decrease the voltage here. So V2 is going to decrease, and of course V1 is going to increase. So of course in a voltmeter, this is what's of concern to you. You are actually decreasing the very value that you're trying to measure. So you're hoping this is a minimal effect, but it is technically true that a voltmeter will slightly depress the very voltage it's trying to measure. You hope in the fifth decimal place where you don't even care, you're not even going to write it on your, you're not even going to write that far down into the decimals on your paper. But it is technically true that a voltmeter always measures a lower value than it was before it got there. There's a cost to knowing. Okay, that's all pretty much review thus far in terms of series and parallel. But that brings me to where I'm really looking to go for this lecture. So here I'm back to the parallel situation. I've drawn the battery like you normally would take it out of the package. It's usually got a plus and a minus label. It's got a high voltage and a low voltage. And then, of course, you plug in some resistor, and for reasons that will become apparent shortly, I'll call it resistor 2. So let's say resistor 2, that is your only resistor so far. Okay. So what do you have? You have one equipotential here. That's the high voltage. You have another equipotential here. That's your low voltage. And again, I haven't connected R3 yet, but in anticipation of doing that, I will kind of include that. But the point I'm trying to make here is that the voltage of the battery, the voltage drop from here to here is the same as the voltage drop across R2. And if I added a third resistor, R3, that would be the same. So here I have the voltage across the battery is the same as the voltage of 2. And should I choose to add 3, that would just be another voltage across that. Now you may notice I'm using VBAT. I'm not using the EMF character anymore. So that's of course been the sacred character that I use for battery voltage. But here I'm just going to call it voltage of the battery. Okay. So let's take a look at what adding R3 would do. Now remember all the way back here on the first page, if you have this normally situation, if you add another branch, then this branch does its own thing regardless. Okay, so it still has full access to the battery voltage. It's still its fixed resistance. That means it has to have the same current and same power. So this bulb, if this is a light bulb, should not have any effect. In a parallel circuit, every branch is kind of its own lone gunman thing that it does by itself. It doesn't care if there are other branches. So we expect that the voltage drop and the power of this resistor is going to be unaffected. Okay, so here we have a surprise. Okay, that's not what really happens. Okay, actually V2 and P2 are both decreased. So in other words, if this was a light bulb, it would get dimmer with the addition of a new branch. So what the heck is going on it's not behaving like this, where every branch is independent. It is actually behaving a lot more like this series circuit. So it's behaving like what would happen if you had an R2 here and you added an R3 in parallel. The voltage drop available here is decreased and the power is decreased. So it's acting more like this. So what's the deal with that happening? It's like it's in series with a resistor, but you can't see it. Well, I'm here to tell you that there is a resistor. Okay? So what is actually inside of a real battery? Okay, so what we're talking about here is non-ideal batteries. This is like how batteries really behave in the real world. Okay, this is real world behavior that we're talking about. What can we think of as a battery being made out of? Well, we can think of it as being comprised of an ideal EMF, okay, like that. And then, of course, wherever the charge is generated inside the battery, it still has to make its way out of the casing. And so what happens here is we can account for the fact that there is some resistance just to get the charges out to you, the consumer. So I'm going to call this lowercase r, okay? And what this is this is called the internal resistance of the battery. Now I want to emphasize, it's not like they actually put a resistor in there, right? That would serve no purpose, but you can't help but have resistance in there, okay? And so what that means is we have to account for the fact that even if you think that your circuit is out here, there is another unseen resistance, the internal resistance of the battery, that you're always in series with. So you're always in series with this. Okay? So it really tells you something very unfortunate. The whole idea of a perfectly parallel circuit is actually not possible. Okay? To have this ideal situation that we're talking about here, where this sort of EMF that is perfectly unwavering is provided by the battery, and you can hook 1 or 2 or 17 different resistors up to it, and they all can kind of feed from that same voltage drop, it's not really possible. A pure, true parallel circuit is kind of like a unicorn or a free lunch, okay? It doesn't really exist, okay? Anytime you have a circuit that you're connecting to the battery, you will always have an internal resistance in series with that, okay? So the way that we could draw that is like this. If we're going to draw it like the other branches, this was R2, and we're adding an R3. And when we add that R3, of course, the voltage drops redistribute. This V2 and P2 are going to decrease, and over here, V1 and P1, this was kind of the role played by R1 before, this is going to increase, okay? And then just as so what we can now understand is when you connected R3 in parallel, it's affected how much resistance was here versus here, so the voltage drops redistributed. So as we said, the voltage 2 and P2 actually decreased. You can see that here, okay? And so if this was a light bulb, you would see this is dimmer, okay? So it sort of makes it so that even when you think you have a parallel circuit, when you do add new branches, they do affect the previous branches, because you aren't really in parallel. These are in parallel, but they're in series with something, a resistor, that you can't even see, okay? Let's go ahead and circle the equipotentials here. We can still kind of treat this resistance exactly like we would in any other circuit. So don't worry about the fact that it is trapped inside the battery and you can't see it. As far as how you would calculate, you calculate exactly the same way. we could go ahead and circle our equipotential regions here. I'll call this A, okay? And this one I'll call B, this one, middle one, and then of course down here we would extend this all the way over here. We have C. We just have our classic series circuit. We have a high, middle, and low steps, okay? So let's take a look at what that looks like. So here we have it. We have our, let's put our labels here. We drop some voltage across the internal resistance, and then we drop the rest across the circuit. Whatever you think is your actual circuit that you're connecting up is really connected in series with the internal resistance. And of course, the voltage drop from beginning to end still has to be the same. You have this sort of ideal EMF of your battery that you can't even really access because you will drop some of that voltage before you ever get out of the casing. Okay, I want to point out here in this previous page, okay, that the voltage across the battery here, right, you literally are connecting the two, you're touching the two terminals. That is the voltage from B to C, okay? So the voltage across your battery, and that's being applied to across resistor 2 and resistor 3, okay? The voltage across the battery and the voltage across your circuit, that is from B to C, okay? So that's why I sort of switched to calling this the voltage of the battery, because the voltage that you can actually measure across the battery isn't actually this ideal EMF, okay? This ideal EMF of the battery you can never really have access to, because remember that you lose some of it before you ever come out of the battery casing, okay? So notice that this equipotential region A is trapped inside the battery. It's inside the casing. What you actually have access to measure across is B to C, okay? So that's what a non-ideal battery is actually made out of. An ideal battery, or sorry, a non-ideal battery, you can think of it as having an EMF that's ideal, that you never really can measure, and it has an internal resistance such that you lose some of it on your way out, okay? So, let's work out the details here. So for the internal resistance, how much voltage are we really losing across it? I'll apply V equals IR. The voltage drop that you lose across the internal resistance here, and I'm calling the resistance of that little r. It's generally very small. We'll find out. And then, of course, we can use the total current because, of course, the total current, it hasn't had a chance to split off yet. The total current will always flow across that internal resistance. And so if we go ahead and we put this in here, and then we remember that the voltage of the battery and the voltage of the circuit is here, if we were to solve for that, we'd get, moving this over to the other side, that the voltage that you actually can measure across your circuit and what you think is the battery voltage, so that's B to C, okay, that is actually the EMF minus what you already lost here. So that right there, that's the amount you lost, okay? So this is what you lost before you ever got out of the battery casing, and you have now the ability to apply it to your circuit, okay? So in summary, over here, what is the voltage you can actually measure across the battery terminals? It is the EMF, this ideal EMF that you don't even really have access to, minus the amount you lose before you ever get out of the battery, that's across the internal resistance. So, how does this work out in practice? So, hopefully something like this, okay? So hopefully this is very minimal, okay? So if this ideal EMF that's inside there is like, I don't know, 9 volts, maybe you'll lose 0.1 volts across that internal resistance, and you have 8.9 volts that you can apply to any circuit. And you can see, of course, that these are pretty similar, okay? So it might even say, well, those are close enough, why do we even bother with this, okay? And that's certainly true. if you might even say, why don't we just say that the voltage of the battery is 8.9 volts? Why do we want, if that's what we have actually access to applying to circuits, why don't we just call it an 8.9 volt battery? If this ideal 9 volts, you can never actually access it, right? Here's the issue though, you can't just subtract off this and then slap a label on the battery and call it 8.9 volts. It's the amount changes, okay? So this amount that you have to take away is not fixed. It depends on the total current. So if your total current is small, right, or your internal resistance is extraordinarily small, then it's basically you're not taking very much, then the voltage across your battery that you have access to is pretty much the same thing, right? So that's kind of what I was drawing here, right? So 9 volts, 8.9 volts, right? These are pretty much the same. That's what you hope in most instances to be the case, okay? However, remember that if we take our circuit, and our circuit has a very, very small resistance, then it's going to give up a lot of voltage, and it's going to give a lot to the internal resistance. So that would be a scenario where you are really dropping most of your voltage, so across the internal resistance. So example, let me label these equipotentials again. Maybe this is a 9 volts again, but maybe you are plugging in some circuit that's really, really, really small resistance. And if that's the case, this might drop to, I don't know, 1 volt. And this might be 8 volts over here. So again, this is decreasing its voltage, and it's giving up to others, right? So less voltage over here, more over here. Now remember that if this voltage on the first piece decreases and power and the voltage over here increases, the powers go the same exact way. So you are going to be dissipating a lot of power over here as well. Now, that is the last thing you want to do, is be dissipating power inside the battery. You're dissipating power inside the internal resistance of your battery. So that is, your battery's going to get hot. I'm sure you've experienced batteries when you plug them into things where the resistance of the circuit is very low. The battery gets hot, and in fact, this could be dangerous, okay? You could overheat it. So that's where overheating batteries comes from. It essentially comes from you're plugging them into circuits that have a very, very low resistance. You're drawing a ton of current, okay? Remember, when Req goes down, I total shoots way up, okay? So you have a lot of, if you look at this, you will have a lot of power dissipated in the internal resistance, okay? So that right there, that is bad news if your battery is not equipped to handle it, okay? And what you notice here, if the total current is large, then the voltage across your circuit and that you measure across your battery can be significantly less than this ideal EMF, right? Here, your ideal EMF, which again you can't really have access to, is 9 volts. You drop 8 volts of that before you ever get out of the battery, and you only have 1 volt left to apply to your circuit, okay? So, not only are you causing a dangerous situation by dissipating so much power inside your battery, but you are actually not able to have the voltage that you're actually applying to your circuit be very much. So again, remember, how close these two are to each other depends on this term right here, okay? So you could, ideally, you would barely drop any voltage across the internal resistance, and you'd have most of it available to apply to your circuit, but that depends on the circuit. If the circuit is really, really low resistance, you're actually going to drop most of the voltage before you ever get out. So let me give you an example of this. Now if you use sort of a normal Duracell battery, and in the series and parallel circuits lab, you usually, that's what you use. So you will see that as you go from one light bulb to 3 bulbs, of course, you are going to make the circuit more and more low resistance. You will expect that these first bulb will get dimmer. You can see it, okay? Remember over here, the voltage and power is going to decrease across whichever bulb was in this first thing, right? So it's exactly the same as this situation right here. So this bulb will decrease voltage, decrease power. If this is a bulb, it will get dimmer because you're losing voltage over here and you're putting it over here. So you can see, even for a Duracell battery has a pretty significant internal resistance. And so you can see this effect. Now, this is why I did not use a Duracell battery for all my circuits demos. As you can remember, I use a car charger, which at the time seemed like total overkill, because why am I using a car charger to light up some little light bulbs? Okay, it's like shooting a mosquito with a shotgun. Well, in that case, when I went from 1 bulb to 3 bulbs, you did not see much of a dimming effect, okay? And the reason why you didn't see that dimming effect is because a car charger, of course, is normally having to source huge amounts of current, right? Huge amounts of current, and so they are built with a very, very low internal resistance, okay? And so, for the car charger, the voltage of the battery for the scenario that I was doing is very close to the EMF, okay? So there was a very minuscule voltage drop across that, but pretty much what I had to apply to my circuit, whether it was 1 bulb or 3 bulbs, was pretty much the whole voltage, okay? So essentially what I did was I tricked you into having you think that a pure parallel circuit could even exist. That demo was basically to try to show you the basics of parallel circuits. But of course, this battery, there's no such thing as an ideal battery. This battery was so good that with a car charger, the internal resistance is really small, and so the battery voltage pretty much stayed constant whether I connected 1 bulb or 3 bulbs, okay? So that's part of teaching. Sometimes you kind of just you know, try to simplify the situation as much as possible so that you can learn something, and then later on you can say, well, it's not quite like that. And by the way, even for car chargers, I can sort of sweep this effect under the rug. You don't see the first bulb dimming when I add more in parallel. But even then, if you start to go up to much higher currents, like they're actually used in cars, you can see this effect. So an example would be, and this is one of your homework problems, this circuit initially is just the headlights of your car. And then you put the headlights and, sorry, this is headlights and your starting motor. So, sorry, I don't have any space, but so it goes from headlights to headlights and starting motor. So those in parallel do drop the resistance of the circuit quite a bit, and it will lower the voltage drop here and increase it over here. And so one of the things you can see when you're starting your car, especially in older cars that can't compensate for this, the headlights will dim while you're starting your car. So that's a perfect example of this previous situation we keep talking about. When you have your headlights and you put the starting motor in parallel, this P2 will decrease because this voltage decreases and this power decreases across this resistor and it puts it over here, and you're of course taking more of the voltage drop across your internal resistance. So as far as how to calculate with this, I don't, there's not really, aside from this concept, there's not really a whole lot that you need to do. Just understand that you're adding a new resistance in series with the rest of your circuit. And then you just calculate exactly how you would. Just remember that that resistor that's in series with everything is actually inside the battery. So when it asks you the voltage across the battery terminals, it's not actually asking you for this EMF, it's asking you for the voltage that's left over. So this ideal EMF minus what you lose here, that's actually the voltage that you can measure across the battery terminals.